Okay, in this video, we talk about control volume energy conservation analysis. Let's first revisit the energy balance equation of a system in general. The conservation of a system's energy is like this. We consider the change of a system's energy. That change is equal to the difference between the energy that goes into the system and the energy that comes out of the system. And there can be various forms of energy transfer across the boundary of the system. And also, we should also know the energy of the system itself includes internal energy, kinetic energy, and potential energy. Now, let's switch to the energy balance for a control volume or control volumes. The general energy balance equation still applies. However, we need to know what the energy transfer forms are that's associated with a control volume, especially the energy transfer that's due to mass entering and leaving a control volume. Let's compare the energy balance equations. For a closed system, it is the first equation that's boxed in the blue box. The change in the system's energy, internal energy, potential energy, and the kinetic energy all combined is equal to the difference between these two terms, Q in and W in minus Q out and W out. That's heat transfer and the moving boundary work for a closed system. Okay, for an open system, it is still the energy change of the system. Now the box moved to this equation for the control volume. The energy change of the control volume, still internal energy, potential energy, and kinetic energy combined for the system is equal to these two terms in parentheses, Q in, W in plus E mass in minus Q out, W out, and E mass out. The subscript CV stands for control volume. The difference here, comparing the two equations, is for the control volume, we have a E mass term. Now let's do a comparison using this table. For closed system and the control volume or open system, heat, work are both there. Both heat and work are possible for both types of systems. However, the form of energy transfer due to mass flowing across a system boundary is only possible when you have a control volume or open system. This type of energy transfer is not possible for a closed system. It's not there for a closed system. So here I want to highlight this flow work. Look at the bottom right corner of the table. What is flow work? Flow work is this. Imagine you have a control volume like drawn. Let's draw here. This bulky part is the control volume, and think of a parcel of fluid that's entering the control volume. It pushes its way into the control volume. Now, certainly it's because the fluid behind it that's pushing it into the control volume, and this parcel of fluid pushes its way into the control volume. You have force F. You have the distance that's traveled by the fluid, a very small distance traveled by the fluid, and that is work. Force times distance, that's work. So this results in work done on the control volume by the flowing fluid entering the control volume. And so this is the expression of the work done. And we can normalize that work onto per unit mass of flowing fluid. So that's flow work. Flow work is equal to the work done by the parcel of flowing fluid entering the control volume divided by its mass. And as a result, the flow work per unit mass of flowing fluid is the product of pressure and the specific volume. So that's flow work, PV, V lowercase. Now, the physical meaning of flow work is that it accompanies the flowing fluid and is always received on the downstream side of the boundary. So therefore, when the flowing fluid would bring in flow work when it enters a control volume, And when the flowing fluid leaves the control volume, it actually takes away the flow work out of the control volume. It is also called flow energy because it's part of the energy that is associated with a flowing fluid. Now, let's think of the energy transport by mass. That is flowing fluid entering or leaving a control volume. The energy that's associated with a flowing fluid about a control volume includes these things. It's the internal energy, potential energy, kinetic energy, plus flow work. Okay, now we know you can combine U and PV, this first term U and the last term V, to become enthalpy. Now, that's by definition. We learned that before. Enthalpy is defined as U plus PV. So we can write the theta, this energy per unit mass that's carried by flowing fluid, as H plus PE plus KE. So the energy associated with a flowing fluid entering or leaving a control volume is its enthalpy and its potential energy and its kinetic energy. Three things. Okay, now again, we can think of the energy transfer by mass in different perspectives. Now, the extensive energy that's carried by flowing fluid entering a control volume, if you know the mass of a flowing fluid entering the control volume, then it's m times theta. If you think of the time rate of energy transport by mass, then you need to know the mass flow rate of the flowing fluid. That'll be over m over dot times theta. Theta being the energy carried by the flowing fluid on a per unit mass basis. Okay, and then you can expand that to show that theta is actually equal to enthalpy and kinetic energy and potential energy. So now we can complete the energy balance equation for a control volume. Now, first, think of the energy change of a system. I have two equations here. The top equation is the general equation. You have the change of a system's energy, which is equal to E in minus E out. If you take the time derivative of on both sides of the equation, you have the time derivative form, which is the second equation. The second equation can be expanded into this long equation. This long equation is this. Basically, I expand E over dot in and E over dot out. E over dot in is equal to the heat transfer in work done onto the control volume, that's through shaft work, and the sum of energy transport terms into the control volume due to various streams of flowing fluid into a control volume. Now, likewise, the E over dot out of the control volume has all these terms, except the direction of the energy transfer is different. It's out of the control volume. You count all those terms. The subscript I and J represent the individual inlets and outlets. Now, in this course, in most cases, we only have one inlet and one outlet. So in the sigma, in the sum term, there's only one item, either in or out. Okay, we also know in considering energy conservation of a control volume, we also need to consider mass balance. I have a separate video in this playlist that considers mass balance, mass conservation of a control volume. I'm not going to elaborate here. Okay, so the energy balance of a steady flow processes, that's a special form of a special type of energy conservation situation about a control volume. That's when you have a steady flow process. The equations that I introduced prior to this slide apply to general situations, whether you have a steady flow process or a transient, unsteady flow process. So in a steady flow process, the properties within a control volume or the extensive and intensive properties within the control volume don't change with time, even though they may vary with location. That's generally the case. The properties do vary from one point to another point within the control volume. So the mass, the energy inside a control volume, and the volume of a control volume are all constants in the steady flow process. So as a result, we have this equation. These two equations. These two equations are necessary for a analysis of energy conservation analysis of a control volume. The first equation is about energy. The second equation is about mass. And that's because in the control volume, these things, the mass, the energy within the control volume don't change with time. Okay, in the steady flow process, the energy conservation equation is like this. One thing I would like to highlight is that the work in the steady flow process is only shaft work. It's not the moving boundary work, because in a steady flow process, the volume of the control volume does not change, so that the moving boundary work has to be zero. Okay, now let's focus on this one inlet, one outlet steady flow process, which is the case for almost all of the problems that you will encounter in this introductory thermodynamics course. Okay, the energy balance equation is like this. Now this is rearranged from the previous equations. And then the previous equations, in the previous forms of the equation, I have shown you what's going into the control volume must be equal to what's going out of the control volume for a steady flow process. Okay, now I have rearranged that equation so that the terms in and out appear on both sides of the equation. This is to focus on, this is basically separate. Now you see on the left-hand side of the equation, it's the heat transfer form, and it's the shaft work items of energy transfer. On the right-hand side of the equation, all these terms are energy transport terms related to mass crossing the boundary of a control volume, flowing fluid crossing the boundary of a control volume. Or equivalently, we can write this. We can write the heat into a control volume minus the net work. Okay, net heat into a control volume minus net work out of a control volume is equal to the change in the energy transport into the control volume and out of the control volume related to mass crossing the boundary. So delta H, delta Ke, delta P refer to the difference between the enthalpy, kinetic energy, potential energy between the mass going into the control volume and going out of the control volume. And certainly we also always need to consider the mass balance equation when we analyze the steady flow, when we analyze the energy conservation of a steady flow process of a control volume.